So chapter 3 is about exponential and logarithmic functions. And in section 3.1, we're really just going to look at those exponential functions and what their graphs look like. So we'll talk about exponential functions that have the base a and then what that graph looks like. And then also talk about exponential functions with the base e and then what that graph looks like. And then use those exponential functions to solve some real life situations. So for the first thing, just the reminder that when you have an exponential function with the base a, what makes it exponential is that it has a variable, VAR, it has a variable in the exponent. So with a variable in the exponent, that's what makes it exponential. If you have a number in the exponent, then you have a polynomial or some sort of power function. Your base, the a value, will always be greater than 0. And it will never equal 1, because if you had 1 to any power, you would get 1 and you wouldn't have any sort of growth or decay. So when we look at this first example, we're using a calculator just to kind of get the hang of typing in exponential functions. So the first one, when you type in 2 to the negative 3.1, you should get, we're going to go 3 decimal places, 0.117. The next one, if you do 2 raised to the negative pi, you get 0.113. This one, when we plug in 3 halves for x, so 0.6 raised to the 3 halves, you end up with 0.465. And then that last one, 1.05, and this one it's raised to the 2 times 12. So make sure you include both of those in your exponent. You should get 3.225. So when we're looking at the graph of an exponential function, when we have a to the x, you have these two graphs here, just as examples. We have 2 to the x and 4 to the x. And if you notice, when that base is bigger, your graph grows more quickly exponentially. When you plug a 0 in for x, your y coordinate will be 1, because anything to the 0 is 1. So if you had 2 to the 0 or 4 to the 0, your y coordinate would equal 1. So your exponential function will always cross at that 0.01. And then depending on if you have growth or decay, if x is positive, we have growth. And so we have this horizontal asymptote at the x-axis. Right, so we would say that as x is approaching negative infinity, our function would be approaching 0, and that's for when your x is positive. So looking at that, just a few things to know. The domain, in this case, we have a to the x when a is greater than 1 and x is positive. Our domain is all real numbers. Our range is 0 to infinity. Notice we're not including the 0 because that's that horizontal asymptote. The only intercept you'll have is at the 0.01, and it's increasing on the entire domain. When x is negative, we still have the same domain, range, and intercept, but this time instead of increasing on the domain, we would be decreasing. So when x is negative, the graph would look more like this, where when x is positive, your graph would be increasing. So again, that graph of exponential functions, it's that horizontal asymptote as a to the x approaches 0. So as our graph gets closer and closer to 0, our x coordinates will be getting closer and closer to negative infinity. When a to the negative x is approaching 0, our x coordinates are getting closer and closer to positive infinity. These are both continuous functions. So when we're using these and maybe looking at transformations, remember that your x values lie. So they're doing the opposite of what they're saying that they're doing. So if your transformation is connected to the x value, it's not actually doing what it's doing. And your y values, or your y's, right? We use the word y's kind of as a play on words. It means that they're telling the truth. So whatever it says that they're doing, they're actually doing. So in this first one for a, when x plus 1. So the plus 1's connected to the x. So instead of moving in the positive direction 1 along the x-axis, we're going to say it's going to shift to the left 1. This minus 2 isn't connected to the x, it's down connected to the y. So this would shift down 2. This negative out here, again, it's not up with the x. So that's going to be reflecting your y values. And if you're reflecting your y values, you're reflecting them over the x-axis. And then the next one, the negative, is connected to the x. So that one, you're reflecting your x values over the y-axis. And then the next thing we're going to talk about is the base e. So remember, e is just the number 2.71828. It's on your calculator if you do the second divide. So if you use your second and then divide, that's your e button. And so when e is our base, again, it's still a number, and it's a number greater than 1. So we're still going to have, for e to the x, for this natural exponential function, it's still going to be exponential growth. So when we're using this in our calculators, just some practice, we're going to evaluate e to the x, and then we have our different x values. So for a, when you're evaluating e to the negative 2, you should get 0.135. And when you're evaluating e to the 0.25, you should get 1.248. And then e to the negative 0.4, we should get 0.670. And then e to the 2/3, you should get 1.948. So just that practice with your e button. And then the last thing are the applications for this exponential growth. We deal with this a lot in money and in half-life problems. So this first one with money, we have the compound interest, where we're compounding a certain number of times a year. So your A in both of these, your A is your total amount. Your p-value is your initial amount. Your R is your rate, and it needs to be written as a decimal. The N is the number of times that whatever you're investing is compounded per year. And then your T is your time in years. And so the same is true for when you have your continuous compounding, but that one, because you're not compounding a certain number of times, it's just continuously compounding, you use the PERT formula, where you'll use E as your base. So if we were practicing those, we have a total of $9,000 is invested at an annual interest rate of 2.5%, compounded annually. So compounding annually means that our N would equal 1. Our initial amount is $9,000. Our interest rate as a decimal is 0.025, and our time is 5 years. So if we're plugging all of that in to find our total amount, we would say 9,000 times 1 plus 0.025 over n, which in this case is 1, and then raised to the n times t. So if you go through and you actually calculate that, you should get $10,182.67. So for example 9, we're doing something similar, but in this case we have two scenarios. A is compounded quarterly, so that would be our N is 4. And B, we're compounding continuously, so in that case, because it says continuous, we'll use the PERT formula. So to start with A, we want our total amount when we invest $12,000 at 3%. compounded quarterly for 4 years. So if you calculate that, you get $13,523.91. For Part B, we're using the same numbers, 12,000, but now we're compounding continuously. And what you find is that when you compound continuously, we have $13,529.96. You actually end up earning a little bit more money because you're earning more interest on the interest that you've already earned. And then our last example is our radioactive decay. It's really your half-life. So something that you should know is your general half-life formula. So your half-life formula is whatever you end up with is your Y. Your initial value we're going to call Y sub 0. 1/2 is our base, and we always raise it to the total time over the length of the half-life. All right, so your Y sub 0 is your initial amount. Your T is your total time. And the H is the length of the half-life. And so if we were to go through this, they set up this equation for us already. So in part A, where it says, what is the initial mass? When we look at it, that's that number out front. So our initial mass is 10 grams. And part B wants to know how much is present after 80 years. So that's our total time, which means we'll plug in an 80 for T. And then we're dividing by 29 because that's the length of the half-life when you read that scenario that they gave us. And so then what you find is that after 80 years, you have 1.478 grams of strontium left.